Welcome back to the second half of section 5. Let's do some examples. As you drive in your car at 15 meters per second, which is just a bit under 35 miles per hour, you see a child's ball roll into the street ahead of you. You therefore hit on the brakes and come to a stop as quickly as you can. In this case, you come to a rest in 1.5 seconds. How far does your car travel as you brake to a stop? Well, the one thing that I really like and I encourage you to do is when you get a problem like this, a word problem, is you identify all the pieces of information and you make note of them, circle them and tabulate them, make it all organized. So I'm driving in my car at 15 meters per second. That to me sounds like some initial velocity, 15 meters per second. Just a bit under 35 miles per hour. It's probably superfluous information. I then hit the brakes and stop as quickly as I can. In this case, I come to a rest in 1.5 seconds. That time sounds like a time interval, how long it takes me to stop. How far does my car travel as I brake to a stop? Well, that sounds like it's asking for a displacement. So I can basically draw a motion diagram that shows first I'm cruising along at a constant speed. And then here I see the ball and slam on my brakes. So my velocity vectors get smaller and smaller until I come to a stop. So that's maybe half a second, 1 second, 1.5 seconds after I start my clock, which is when I see the ball. Okay? So I can solve this graphically, or another thing I can do, I can make a graph, a velocity graph. Let's draw another axis down here. So I've got my x-axis, oops, I'm sorry, this is time. Let's get rid of that real quick. And delete that. Okay, so this is my horizontal axis is time in seconds in this case, and my vertical axis is velocity. Let's make the velocity graph in meters per second. Those are the units. Okay, so here's the origin. That's half a second. Here's 1 second. It's 1.5. There's 2, and so on. And vertical, I have my velocity. So I start at 15. So let's do like 5, 10, 15 meters per second. And that's how I start. And it takes me 1.5 seconds to come to a stop. So let's draw a line. Good. Okay. So this is a graph of my velocity as a function of time. Now there are several ways I can solve this problem. I can do it algebraically, or I can do it graphically by finding the area under this graph. Since we've done already some examples using graphs, let's use some equations. Okay, so in this case, I'm going to use my definition of acceleration, which is how much my velocity changes in some time interval. So my velocity, so this is my final velocity minus my initial velocity divided by some delta t. Now if I go back, my final velocity, well, what was my final velocity? I didn't say. Well, I know I came to a stop, so I can add this to my table. My final velocity was 0. Oops, too far. So my final velocity is 0, and then I need to put in my negative initial velocity. So my initial velocity was 15 meters per second. Don't forget this minus sign. Divided by my time interval, 1.5 seconds. My acceleration is then 15 over 1.5 is negative 10 meters per second squared. Now that I have my acceleration, I can find how far I traveled. So using this equation of motion, x final is equal to x initial plus v sub x initial delta t plus 1/2 a sub x delta t squared. I now have all the pieces of information that I'm looking for. I am looking for x final minus x initial. I know my initial speed, I know how long I've been traveling, I know my acceleration, and again, I know my delta t. So x final minus x initial is what I'm looking for. That's my displacement. Now I just moved this over to the left-hand side. Now I can just plug in numbers. My initial velocity was 15 meters per second. I was traveling for 1.5 seconds, plus 1/2, that's a plus sign. My acceleration is negative 10 meters per second squared. And again, I have 1.5 seconds squared. So this left-hand side, that is my displacement. That's what I'm looking for. The right-hand side, I can plug that into my calculator. And what you should end up getting, you can double check my math, you should get something like 11 meters. So this is about, you always want to think about your answer. Does it make sense? Is it reasonable? 11 meters, well, a meter is about a yard. So this is going to be somewhere in the order of like 35 feet. Well, that seems pretty reasonable for how long it takes a car to come to a stop, or how far it goes before it can stop when you're going at a reasonably small speed. Okay, so that seems good. Let's do another example. A drag racer starting from rest travels 6 meters in 1 second. Suppose the car continues this acceleration for an additional 4 seconds. How far from the starting line will the car be? Well, once again, I'm going to pick out some key information. So first of all, the drag racer travels, delta x is equal to 6 meters in a time of 1 second. Suppose the car continues this acceleration for an additional 4 seconds. How far from the starting line will the car be? Well, it's hard to get your head around. What exactly am I looking for? Okay, so if I want the total time, we're given a second piece of information here, time. So let's call this delta x1 and delta t1 to show that these two correspond to each other. And then delta t2, total time will be what? If he travels for an additional 4 seconds on top of the 1 second, the total time is 5 seconds. How far from the starting line? They're asking for the total displacement. And that's delta x2 then, which corresponds to delta t2. So the total displacement corresponds to the total time, whereas he accelerates to 6 meters in only 1 second. Okay, so I can do this graphically. I can do this algebraically. I can also do this because I know that how much my displacement changes is proportional to time squared. So in other words, since I'm comparing two times, one that is 5 times the other, so 5 times my initial 1 second gives me the total time, my displacement will change like the square of this. So 5 squared times delta x1. So, well, what's 5 squared? That's 25. So my unknown displacement in this case is 25 times, what was my delta x1? That's 6 meters. And what's 25 times 6? That's 150 meters. So that's a nice simple way of solving this problem, recognizing that my displacement changes like the square of the time. Okay, so that is all the examples I have for this section. Thank you for paying attention.